In this video, we're going to introduce the inverse functions for sine, cosine, and tangent. So as we start to use trigonometry in applications, being able to undo a trigonometric function is going to be an important skill to have. Anytime we have a function and we want to undo that function, we want to reverse it, we use an inverse function. So we want to define these inverse functions specifically for our sine, cosine, and tangent. Now there are some general requirements to find an inverse of a function, not just a trig function, but any function. One of the basic requirements for finding an inverse of a function is that the function you're starting with has to be one-to-one. If you're looking at its graph, it has to pass the horizontal line test. Now this automatically presents a problem. So since the trigonometric functions are all periodic, they repeat indefinitely in either direction. By default, they are not one-to-one functions. If you were to look at the graph of any trigonometric function and draw a horizontal line, it's going to pass through that horizontal line multiple times, which means if you identify a particular y value, well, it matches up with multiple x values, and that by definition means it's not one-to-one. You need for a function to be one-to-one in order to find an inverse, because the idea with an inverse is that you're taking your x and y and you're inverting them. Well, if there are multiple x's corresponding to any particular y, then how do you know which one you're going to choose when you invert x and y? And the answer is you don't. So to address this issue with these functions not being one-to-one, we're going to place a restriction on the domain, the set of x values, the set of inputs for each of our trig functions, so that we get all possible function outputs corresponding to those inputs. We get all the possible outputs we could get for that whole trigonometric function. In other words, we cover the whole range, but we don't get any repeats. So essentially, we want to take a snapshot of our function. We want to take just one section of the function, one particular section of x values that are going to correspond to all the possible y values, all the possible outputs that we could get for that function. But each y value, each output represented uniquely, represented only one time, where no outputs are repeated. In other words, we're going to take that particular function, whichever one we choose, and we're going to restrict it and take just one section of the function so that that one section of the function is one-to-one. And we're going to think of it as sort of a representative portion that represents the whole graph, but it's a one-to-one section where there aren't going to be any repeats. Now, these are going to be some very important distinctions to make as we start to think about what an inverse function is and specifically what an inverse trig function is. What we want to think about is domain and range. What do they correspond to when we're talking about trig functions? Well, if you're talking about an actual trig function, sine, cosine, and tangent, the inputs we can think of as angles. That was how we originally thought of them. We input angles. We started with right triangles and defined our trig values in terms of ratios in a right triangle. But specifically, it was the ratios of side lengths in relation to a particular angle. So you apply a trig function and take a ratio with respect to an inputted angle. So we input angles and then we output what we can think of as xy coordinates on the unit circle. So originally we thought of them as ratios in a right triangle, but as we've demonstrated before, the unit circle is just a way of drawing a bunch of right triangles, summarizing all the information about a bunch of right triangles in such a way that things are simplified and the x and y coordinates correspond to the specific values for our specific trig functions. So anytime you have a trig function, it takes an input that represents an angle measure, radians or degrees, and you output something associated with the coordinates on the unit circle, x for cosine, y for sine, and then some combination for the other four trig functions. Whenever we take an inverse of any function, the domain and range switch places. So what you input into one function, that becomes the output for its inverse, and what you output for your original function becomes the input for its inverse. So when we're talking about an inverse trig function, we're going to input unit circle coordinates and output angles. And we're going to focus on radian measures. It's helpful to think of an inverse trig function as asking a question. Here's the question it asks. An inverse trig function asks the question, what angle has this as its trigonometric value? In other words, you're going to have a value of a trig function. And if you're taking an inverse value, it's asking what angle is going to have this as its sine? What angle is going to have this as its cosine? But specifically, what angle within that restricted domain is going to have that particular value as the value for its sine, its cosine, or its tangent. So let's look at these sine, cosine, and tangent graphs, and let's talk about how we're going to deal with this issue of one-to-oneness, the fact that these are not one-to-one. How are we going to make them one-to-one, and what are the domains and ranges going to look like for our trig functions, for our inverse trig functions? So here's a graph of our sine. Okay, we know it starts at 0 for the standard period from 0 to 2 pi. It increases to its maximum, decreases to its minimum, and then once we make it to 2 pi, we've come full circle. Okay, now this is not a one-to-one function. If we were to draw a horizontal line anywhere on this graph, it's going to intersect with the graph infinitely many times because of course, keep in mind, the graph continues out in either direction indefinitely. So what we want is one snippet of the graph where we get all the possible outputs for sine, but no repeated outputs. So we want to take one section of the domain, one specific interval within the domain, one specific section of x values that are going to match up with all the y values we can get for sine, but not represent any repeated y values. Well, ideally, because of all we've talked about with reference angles, the fact that we use reference angles so much and we use them to find values for other trigonometric values for angles, we want to specifically make sure that the interval we choose contains the values from 0 to pi over 2. Since the angles from 0 to pi over 2 correspond to our reference angles, those are going to be fundamental values that we want to keep. So we're going to keep x from 0 to pi over 2 as part of our restricted domain. So we're specifically going to keep this section of the graph. Okay. Now we know the range, the set of outputs for sine go from -1 to 1. So if we keep this section of the graph corresponding to this portion of the domain from 0 to pi over 2, we get all of the outputs from 0 to 1. Well, that's not going to give us all the possible outputs for sine because we know that the range for sine goes all the way from -1 to 1. So we need to keep some additional portion of the domain that's going to give us all of the other outputs that we don't already have represented right there. And we could technically keep any additional portion on this graph that gives us negative y values, that gives us the y values going from -1 to 0. But it's going to make the most sense to choose a restricted domain that's continuous. In other words, if we've already chosen this particular portion of our domain to keep, everything from 0 to pi over 2, is there a section that adjoins to that, another portion of the domain, another interval of the domain, that would correspond to negative x values? And the answer is yes. If you were to take this particular section of the graph and continue not in the positive direction where we would get repeats, notice if we continued in the positive direction, now we have another section of graph that has the same y values, and it wouldn't be 1 to 1. But if we were to wrap back around and continue in the negative direction, and now keep the additional section of the graph going from the interval from -pi over 2 to 0, this particular interval is then going to correspond to all of our negative values for sine. So if we just keep this one portion of the graph, just keep the interval from -pi over 2 to pi over 2, then that one portion of the graph is going to be 1 to 1, number 1, which was the goal. The goal was to find something that's 1 to 1. But notice that if we just keep that one portion of the domain and throw the rest of the graph away, we still get all the possible values, all the possible outputs for sine represented. Everything from -1 to 1 is represented here with no repeats. So this is going to be our restricted domain. We're essentially going to throw away the rest of the sine graph, and we're just going to keep that one portion that is now 1 to 1, but also contains all the possible outputs for sine. So for purposes of defining this inverse function and needing to meet this requirement for being 1 to 1, we're now taking the sine that technically has a domain of all real numbers, and we're going to restrict the domain to this 1 to 1 interval. So our restricted domain for sine is going to be the interval from -pi/2 to pi/2. Just that one interval. And it is going to include -pi/2 and pi/2 because those are the locations where we hit -1 and +1 respectively. Now our range for sine goes from -1 to 1, and that was the goal in taking this restricted domain, is to cover that full range but cover each y value only one time. So our range is going to be -1 to 1. And this is going to correspond to those values we see on the unit circle. In other words, if we look at all the values on the unit circle corresponding to radian measures from -pi/2 to pi/2, well, that's going to correspond to all of the sine values from -1 to 1 with no repeats. So if this is the restricted domain for our sine, and this is the range, then when we invert and find the inverse sine, what we also call the arc sine, it's going to have a domain of -1 to 1 and a range of -pi/2 to pi/2. So whatever we plug into the sine function, we're going to get out of the inverse sine, and whatever we get out of the sine function, those will correspond to our inputs for our inverse sine. And these are going to be our two notations to indicate that we're looking at an inverse sine, what we also call the arc sine function. So sine with a superscript of -1. Sometimes this could mean an exponent. If we see an exponent that's negative, it typically means take the reciprocal. If we're labeling something as a function and then writing it with a superscript of -1, this is the notation for an inverse. So this is the sine function, but inverted. You may remember on your graphing calculator that you have a button that looks like this or a notation that looks like this, and we specifically said that's not the cosecant. It doesn't mean you're taking the cosecant. It's the inverse sine function, which is the function that reverses the operations corresponding to the sine. And sometimes we'll write arc sine instead. Just keep in mind these two things are the same. Inverse sine and arc sine are defined as the same thing. Okay, so let's look at the cosine. How would we define the inverse cosine or the arc cosine? Well, again, we have the same issue as we do with sine. If we were to draw a horizontal line, this function is definitely not 1 to 1. The y values repeat indefinitely. So we want one section of the graph corresponding to each possible output for cosine, but a particular interval over the domain where we're not going to get any repeated values. Now again, we want to keep the portion corresponding to the angles from 0 to pi/2, all of those reference angles. So that particular interval we want to keep as part of our restricted domain. And that particular portion of the domain is going to give us all of the cosine values from 0 to 1, all of those y values. Well, we know cosine can go all the way from -1 to 1. So we also need an additional interval that's going to give us the negative values for cosine. And again, ideally we want it to be one continuous interval starting at one point and ending at another point with no breaks in the middle. So if we were to continue and then look at pi/2 to pi, notice that particular interval is then going to correspond to all of the negative cosine values, taking us from 0 to -1. So we also need to keep that particular interval from pi over 2 to pi. But if we only keep that interval, take just that interval from 0 to pi, and then throw away the rest of the graph, what we're left with is now 1 to 1, and it also corresponds to all the possible y values that our cosine could take on, everything from -1 to 1. So that is going to be the interval we're going to keep as our restricted domain. So whereas cosine technically has a domain of all real numbers, for purposes of defining our inverse cosine, we're just going to keep this portion of the domain from 0 to pi. So our restricted domain is going to be the interval from 0 to pi, including 0 and pi. And then as with sine, the range of cosine is going to be -1 to 1. Again, because of our definition on the unit circle, the maximum and minimum values we can reach are going to be -1 and 1, and we can get any value we want in between. So our range is going to be -1 to 1. When we invert, take the inverse cosine or the arc cosine. Inverse cosine is going to take a value from -1 to 1 as its input. It's going to take a unit circle coordinate as its input, and it's going to output an angle somewhere within this interval from 0 to pi. Here we go. And then last but not least, let's look at tangent. Again, tangent also not 1 to 1, but not 1 to 1 in kind of a different way. Here we have individual separate branches that are separated by these asymptotes. Sine and cosine don't have any asymptotes. But regardless, this function is still not 1 to 1. If you were to draw a horizontal line anywhere on this graph, it's going to cross through the graph at more than one location. So we have repeated outputs corresponding to different x values. So yet again, we want to restrict this domain to one particular interval of values where we get all of the possible outputs, all the possible y values that we could possibly get for tangent, but none of them are repeated. So again, we want to keep the portion from 0 to pi over 2, since that corresponds to all of our reference angles, all of the acute angles that could exist in an actual triangle. We're going to keep that portion. And then we also want some type of adjoining portion, ideally, where we would get the remaining values for tangent. So the range of tangent is actually all real numbers because of the way this graph is shaped. Because it goes indefinitely in both directions, we get any y value we want from -infinity to infinity. Well, this particular interval of the domain is going to give us all of the positive outputs for tangent. And if we keep the adjoining portion of this branch going from 0 to -pi over 2, that's going to give us the remaining negative values for tangent. So initially, this looks like essentially what happened with the sine function. This basically looks like how we restricted the sine function. We took everything else, threw it away. This is now 1 to 1, and it covers all of the possible outputs that we could get for tangent. The biggest difference here, though, is at -pi over 2 and pi over 2, where we cut off, there isn't actually anything there. There's an asymptote there. So this graph doesn't actually reach pi over 2 or -pi over 2. It gets infinitely close, but it's never going to reach it or touch it. So we're technically keeping this particular part, but I'm going to write big parentheses here because technically we're not actually reaching -pi over 2 and pi over 2. So when we write that restricted domain, write that interval representing that restricted domain, we have to indicate that those endpoints are not included. So our restricted domain that's going to make our graph 1 to 1 and still give us all the outputs we need is going to be the open interval from -pi over 2 to pi over 2. In other words, it's the interval with those endpoints, but the endpoints are not included because we know those endpoints correspond to asymptotes and there isn't really any graph there. And then our range for tangent across this domain, we cover all the y values we need, which consist of the y values from -infinity to infinity, all real numbers. And then just as before, when we invert, the domain becomes the range becomes the domain. So we can input any coordinate, negative infinity to infinity, into our inverse tangent, and we output an angle between negative pi over 2 and pi over 2, non-inclusive. So those are going to be our definitions. I recommend at some point get yourself a separate sheet of paper, draw yourself a table, and write in all your domains and ranges for all of these functions so you have them all in one place. This is also a great time to have the unit circle available, particularly as you get used to using these inverse functions. Having the unit circle handy is going to be a good thing so you can find different values and work a little bit more flexibly with these inverse functions. So anytime you see an inverse function, I want you to think of it asking a question. And again, you have to think about, what do my inputs represent? What am I plugging into an inverse function? And what am I getting out of an inverse function? If you apply a regular trig function, you're plugging in an angle, typically a radian measure. We're focused here on radian measures. You're plugging in a radian measure and you're outputting a unit circle coordinate. So for instance, if you took the sine of pi over 4, you're plugging in the angle pi over 4, and you're asking for an input of pi over 4, what would the value of sine be? In other words, what would the unit circle coordinate be that would give me the sine for pi over 4? Well, if we're at pi over 4, the value for sine would be square root of 2 over 2. So that means the sine of pi over 4 would be square root of 2 over 2. When you apply an inverse trig function, you're asking the opposite question. You're plugging in a unit circle coordinate or something related to a unit circle coordinate, and you're asking the question, what would the angle have to be in order to give me this unit circle coordinate? Now initially that seems like it would be a difficult question to answer, because if you look at all the coordinates on the unit circle, we see a lot of repeated values. So for instance, for our sine function, which corresponds to our y values, if we wanted to match up to a y value of the square root of 2 over 2, well, there's two locations on the unit circle that have a y value of square root of 2 over 2. So which one do you want? You're going to want the one that corresponds to your restricted range. So the restricted domain for our original function is going to give you that restricted set of outputs for your inverse function. So for instance, for the sine, what we just looked at with the sine, if we're specifically asking the question, at what angle do I get a sine of root 2 over 2? In other words, what's the inverse sine of root 2 over 2? You want the angle that's going to give you a sine that has that value, but you want the specific angle that's within this particular range, that's somewhere within the interval from negative pi over 2 to pi over 2. Because we only kept an interval where we don't have repeats, there will be a unique angle that corresponds to whatever particular value you're looking at. So if you're asking what's the inverse sine of root 2 over 2, what angle gives me a sine of root 2 over 2, there's only going to be one angle within this particular interval. Because again, we restricted things to this interval for a specific reason. It's so that we got all the values we could possibly get for sine from negative 1 to 1, but we didn't have any repeated values, so that each x value and each y value are matched uniquely. So knowing what ranges of values we're looking at for each of our inverse trig functions is going to be important. So for inverse sine, we're taking values for sine, we're asking the question, what angle gives me that particular value? The angle we get is going to be an angle from negative pi over 2 to pi over 2, specifically in that range. If we're taking an inverse cosine, asking the question, if this is my value for cosine, something from negative 1 to 1, well, what angle gave me that value? The angle you have is going to be between 0 and pi, which again, no repeats, so it's going to be unique x value corresponding to your value for cosine. And then same thing for tangent. If we take the inverse tangent, we're asking if this is my value for tangent, what angle would give me that value? Well, if this is my value for tangent, then the angle that matches to that value is going to be angle between negative pi over 2 and pi over 2. Now, before we try some examples, one thing I want to emphasize now, this is probably the most common mistake that students make when they start looking at inverse trig functions, specifically for inverse sine and for inverse tangent. And we'll look here at tangent, we'll talk about it from that point of view. Look at the interval. It goes from negative pi over 2 to pi over 2. So you could think of this as really being two separate intervals. This is really negative pi over 2 to 0. It's really that interval, which is the fourth quadrant. And then it's also the interval from 0 to pi over 2, which corresponds to the first quadrant. Okay, so matching things to angles in the first quadrant is pretty straightforward. Those are going to be all our reference angles. Those are pretty easy to match. Here's where a lot of students make a mistake. You look at the unit circle and you recognize, okay, I'm looking for an angle that's either in the first quadrant or in the fourth quadrant. Since we're so used to thinking of the angles from 0 to 2 pi, as soon as you look at the fourth quadrant, it's tempting to say, well, I'm looking for an angle between 3 pi over 2 and 2 pi, or 270 degrees and 360 degrees. But here, that's not what we're talking about. We're talking about the fourth quadrant, but specifically a fourth quadrant angle that we get from rotating in the negative direction, starting at 0 and rotating backwards into the fourth quadrant. So for instance, saying that an inverse tangent value is 7 pi over 4, for instance, is not correct. 7 pi over 4 is an angle in the fourth quadrant, but it is not an angle within this particular interval. So when we match up to an angle in the fourth quadrant for our inverse tangent or for our inverse sine, it's going to have to be a negative angle, something from 0 to negative pi over 2, rather than an angle from 3 pi over 2 to 2 pi. We talked about this issue when we talked about coterminal angles. Coterminal angles look the same, but they don't actually have the same angle measure. So negative pi over 4 and 7 pi over 4 will look the same, but they are not the same angle. If you were to type each of those numbers into a calculator, they're completely different numbers. That's essentially the issue here. So we have to make sure when we're matching something to a fourth quadrant angle that it's a negative angle, not an angle from 3 pi over 2 to 2 pi. And we'll encounter this as we look through our examples, and we'll talk about it a little bit more when we see it. So let's just find a bunch of individual values. And again, you may want to have your unit circle handy for the time being so we can reference the values on the circle. So find the exact value. First one, inverse sine of 0. What is this asking? It's asking the question, at what angle is my sine 0? So I'm plugging in a unit circle coordinate. This is the input to this function, and the output is going to be an angle. So it's asking the question, what angle has 0 as its value for sine? But specifically, what angle within this particular interval, what angle within this particular interval from negative pi over 2 to pi over 2 has a value of 0 for its sine? That's the question we're asking. So in other words, we're looking at the first quadrant and we're looking at the fourth quadrant. At what angle within those two quadrants do we have a value of 0 for our sine? Well, we know sine corresponds to the y value on our unit circle. So that means that the angle, the radian measure corresponding to 0 for sine, is going to be the radian measure at 0. So the sine of 0 radians gives me 0 as the value for sine. So sine inverse of 0 corresponds to 0 radians. So if 0 is our value for sine, the radian measure corresponding to that within our specific interval is going to be 0. Now what about a cosine inverse of 0? In other words, we're asking the question, if the cosine has a value of 0, what angle within my specific interval would match up to that cosine value of 0? Now we're looking at inverse cosine. So we're looking at the interval from 0 radians to pi radians. So we're asking the question, over that particular interval from 0 to pi, what angle has a cosine value of 0? And again, if we look on the unit circle, if we're looking from 0 radians to pi radians, we're looking at the first quadrant and the second quadrant. Cosine corresponds to our x value. So the location where we have an x value of 0 is going to be at pi over 2 radians. So that's going to be the cosine inverse of 0. Now what about inverse tangent of 0? Tangent ones are a little bit more difficult to do because we can't look at just x and just y. We have to look at them together. So it's helpful when we start thinking about tangent to think of it as a ratio. So 0 could be written as 0 over 1. That's going to be the best way to think of it. Think of it as a ratio. It's a ratio of 0 over 1. And we know tangent corresponds to sine over cosine. So this is asking the question, at what angle, what radian measure, do we have a tangent of 0? But specifically, if we have a tangent of 0, that means the sine had to be 0 and the cosine had to be 1 or negative 1. It could be positive or it could be negative 1. But specifically, what radian measure within this particular interval will match up to a tangent of 0? Well, the sine, we know the sine corresponds to our y value. The cosine corresponds to our x value. So the radian measure within this interval, where we have a sine of 0 and a cosine that's positive or negative 1, is going to be 0 radians. So it's within this interval, and it matches up to the correct values for sine and cosine. Okay, what about sine inverse of 1? So now we're asking, within the interval of values we want, from negative pi over 2 to pi over 2, what angle has a sine of 1, has a y coordinate of 1? Well, in this case, the angle, the only angle within that range, that interval, is going to be pi over 2 radians. So the angle that gives me a sine of 1 is going to be the angle pi over 2 radians. Inverse cosine of 1. In other words, if the cosine is 1, what radian measure gave me that cosine of 1? Well, the only location on the unit circle where we have a cosine of 1 within our interval is going to be 0 radians. And then a tangent inverse of 1. This is another one that's a little bit more complicated. You can think of 1 as 1 over 1 if you want, but ultimately think of it as same over same. Anything divided by itself is going to give you an output of 1. And we know tangent is defined as a ratio. It's defined as the ratio of y over x. So we want to know where on the unit circle do our x and y values match up in such a way that we get a tangent of 1. But specifically, what angle within this particular range of values is going to give us x and y values that match up this way? Well, the only angle from negative pi over 2 to pi over 2, where the x and y values are the same, is going to be the angle pi over 4. So the inverse tangent of 1, the angle that gives us a tangent value of 1, is going to be pi over 4 radians. Okay? Inverse sine of 1/2. In other words, where on the unit circle within the correct interval do we get a sine of 1/2? Where is the y value 1/2? That's going to be pi over 6 radians. That's the location where our y value is pi over 6 if we're looking in the interval from negative pi over 2 to pi over 2. Okay, cosine inverse of 1/2. If the cosine has a value of 1/2, what's the radian measure corresponding to that? Well, cosine is going to be your x coordinate, so the radian measure within the correct interval is going to be pi over 3 radians. Sine inverse of negative 1/2. Here's where things start to get interesting. The negatives is where it potentially gets a little bit more complicated. So sine inverse of negative 1/2. So we're asking the question, where on the unit circle is our sine going to have a value of negative 1/2? but specifically within the interval that we're looking at, the interval from negative pi over 2 to pi over 2. Well, if you immediately think first quadrant and fourth quadrant, you're on the right track. Okay, you're almost there. So if you're just thinking first quadrant and fourth quadrant, and you're trying to find a sine of negative 1/2, then immediately you may say that's going to be 11 pi over 6, because that's where we have a y value of negative 1/2. Unfortunately, 11 pi over 6 is not correct. Why is it not correct? It's not correct because it's not within the actual interval that we want. The interval that we want is the interval from negative pi over 2 to pi over 2, which means, again, when we think of the fourth quadrant, we're not thinking of it as 3 pi over 2 to 2 pi. We're thinking of it as the quadrant we would get if we started at 0 and rotated in the negative direction. So although 11 pi over 6 has a sine of negative 1/2, it's not actually the angle we want. What we want is the coterminal angle to 11 pi over 6 that we would get from rotating in the negative direction away from 0. So that's actually going to be negative pi over 6. So if we started at 0 and rotated negative pi over 6 units, that's going to take us to an angle that's coterminal to 11 pi over 6, also an angle that has negative 1/2 as its sine. So this is going to be the fourth quadrant, but it's the fourth quadrant as accessed by rotating in the negative direction, not around in the positive direction the way we normally rotate. Now what about the cosine inverse of negative 1/2? Where is the cosine going to be negative 1/2 within our particular interval that we're interested in? Well, we know our cosine is going to be our x value, so we're looking for an x value of negative 1/2, specifically in our interval that's in the first and second quadrant. Well, in this case, the one location within the first and second quadrant where the x coordinate is negative 1/2 is going to be 2 pi over 3. There's no issues with rotating in the negative direction. It's just first quadrant from 0 to pi over 2 and second quadrant from pi over 2 to pi. Okay, inverse sine of root 3 over 2. Where within the appropriate interval does the sine have a value of root 3 over 2? That's going to be at pi over 3. That's where the y coordinate is going to be root 3 over 2. Inverse cosine of root 3 over 2. Where within the appropriate interval does the cosine have a value of root 3 over 2? Well, cosine is our x coordinate, so that's going to be pi over 6. Now let's look at a couple more negatives, and then we'll do some tangents. Tangents get a little bit more complicated. Okay, inverse sine of negative root 3 over 2. Where on the unit circle within our correct interval does the sine have a value of negative root 3 over 2? And remember, be careful. So we're looking in the first quadrant and the fourth quadrant, but to get to the fourth quadrant, we're rotating in the negative direction from 0 to negative pi over 2. So if we want the negative angle in the fourth quadrant that has a sine of negative root 3 over 2, it's not going to be 5 pi over 3, it's going to be the angle that's coterminal to 5 pi over 3. So it's going to be negative pi over 3. And then inverse cosine of negative root 3 over 2, where within the appropriate interval is our cosine, negative root 3 over 2? Well, we're looking from 0 to pi, so within that interval we're in the second quadrant, and the location where the x value is negative root 3 over 2 is going to be 5 pi over 6. Okay, now let's look at the tangents. Again, the tangents are a little bit more complicated because we can't just look at a single coordinate and determine this corresponds to a particular value for tangent. Tangent is defined as a ratio. So it's going to be helpful to take each of these values, root 3, negative root 3, and then negative root 3 over 3, and think of them how we could write them as a ratio. So for the square root of 3, again, I'm going to think of that as root 3 over 1. Now, I don't have a value of root 3 and a value of 1 like this in combo, in ratio on the unit circle. But I do have locations where I have a root 3 over 2 and a 1 over 2. So I'm actually going to think of it as a root 3 over 2 and a 1 over 2 instead. keep in mind, if we took this ratio as opposed to just root 3 over 1, it still simplifies down to the square root of 3. These match the actual coordinates we see on the unit circle though. So we're talking about sine over cosine, otherwise known as y over x. So we're looking for the location within the appropriate interval from negative pi over 2 to pi over 2, where our y coordinate is root 3 over 2, and our x coordinate is 1/2. And the one location where that happens within our appropriate interval is going to be pi over 3. Now, same kind of thing with negative root 3. So it's going to be negative, and then it's going to be root 3 over 2 and 1 over 2. Now the question is, does the negative go with the numerator or the denominator? That is going to be decided by the quadrants we know that we're restricted to. So when we're looking at inverse tangent or inverse sine, we're talking about the first quadrant and we're talking about the fourth quadrant. Well, in the first quadrant, both coordinates are positive. In the fourth quadrant, we have a positive x value, but we have a negative y value. So that means the negative is going to go with the y. So we're looking for a location where our y value is negative root 3 over 2, and our x value is 1/2, but specifically within the interval that we've given from negative pi over 2 to pi over 2. In this case, it looks like 5 pi over 3, but remember it's going to be the coterminal angle that is negative. So that's going to be negative pi over 3. And then one more. This is going to be the challenging one. We don't have anywhere on the unit circle where there's a root 3 and a 3 as a ratio. What this is right here, this is a rationalized version of a value for tangent. So let me go up here and do some work with this one just a little bit. So we have negative root 3 over 3, which again is a rationalized version. So think of rationalizing this backward. Instead of rationalizing the numerator or denominator, what if we rationalized the numerator? This will take us backwards to the version of this number that we get when we actually just take ratios as is. So our numerator is going to become 3. We still have that negative. And then our denominator is going to be 3 root 3. So those 3's are going to cancel out. So we're left with negative 1 over root 3. But again, we don't have just 1's and root 3's, but we do have 1/2 and root 3 over 2. Again, tangent is defined as our y over our x. And since we're looking within the interval from negative pi over 2 to pi over 2, first quadrant, everything's positive. Fourth quadrant, x is positive, but y is negative. So the y is going to be the negative. So in other words, we're looking for that angle, that radian measure from negative pi over 2 to pi over 2, where the y value is negative 1/2 and the x value is root 3 over 2. It looks like 11 pi over 6, but the coterminal angle in our interval is going to be negative pi over 6. This is going to definitely be one you want to practice with. Spend some time practicing with these. Get another sheet of paper, do them all over again. Make sure you can determine looking at the unit circle, but try not to become super dependent on the unit circle because you're not going to have it there forever. Being able to visualize the unit circle is going to be an important skill to have, particularly when it comes to doing these kind of problems where you have to reverse the process. Now, depending on the situation we're in, how we're using our inverse functions, we may just need an approximation just like we approximate actual trigonometric values. So your calculator can handle these as well. So make sure you have your graphing calculator out. And let's look at how you would evaluate these in your graphing calculator. Now, just as we can plug in degrees and radians to a trig value or to a trigonometric function, we can output both degrees and radians when we're talking about an inverse trig function. So just as we have to adjust the mode for a trig function, we also have to potentially address the mode for an inverse trig function, depending on what kind of angle measure we want. So our directions here are to get both angle measures. We're going to approximate these, and it doesn't say anything about rounding, so let's round to 4 decimal places. Now we want to approximate in radians and in degrees. So let's start with radians. So go and check your mode. Make sure you're in radian mode. Okay. So the first thing we want is an inverse sine of 1/4. Now right above the sine button in blue, it says sine with a superscript of -1. That's going to be your inverse sine. So because it's in blue, you're going to hit second first and then sine, and then type in your input. And again, keep in mind what this represents. 1/4 represents some coordinate on the unit circle. It's a coordinate of 1/4 on the unit circle. We don't have 1/4 labeled on the unit circle, but it's there. It's somewhere there. We're saying the value for sine is 1/4. Well, what would the angle have to be within our particular interval to give us a sine of 1/4? That's the question we're asking. And in radians, that angle is going to be roughly 0.2529. So approximately 0.2529. And again, that is in radians. And we'll do the degrees all in a minute. Let's do all the radians first, and then we'll go back and do the degrees. So for the next one, we want an inverse cosine. Same idea. Here's your cosine. Cosine with a superscript of -1. So second and cosine. And we're evaluating at an input of -3/8. So again, we're asking the question, if the cosine has a value of -3/8, in other words, that's the unit circle coordinate corresponding to cosine, well, what would the radian measure have to be to give us that value for cosine? And in radians, that's approximately 1.9552. 1.9552. So this would be an angle in radians. This would be an angle that's in the second quadrant. This would be an angle that's in the first quadrant. Okay, and then one more, inverse tangent. So second and tangent of 7/5. Again, we're asking the question, where on the unit circle, what radian measure gives us a tangent value of 7/5? In other words, if we take the ratio of sine over cosine, of y over x, where do we get a ratio that's equivalent to 7/5? And in radians, 0.9505. Now let's do it again in degrees. Degrees are typically a little bit more meaningful if you're trying to visualize. So let's go back into the mode menu, and now we're going to adjust and put it in degree mode. And then we're going to repeat. So it's asking the same question, but now it's asking for a particular angle on the unit circle in degrees rather than in radians. So inverse sine of 1/4. In other words, if the sine is 1/4, what degree measure would that correspond to on the unit circle that would give us a sine of 1/4 in our chosen interval? And in degrees, that's going to be 14.4775 degrees. So 14.4775 degrees. You might be asking the question, well, why don't I just take the radian measures and do the conversion to degrees? You certainly could, but this will probably save you some time just putting it back in the calculator. It saves you time that way. Okay, inverse cosine of -3/8. So in other words, again, we're asking the question, if the cosine is -3/8, if that is our x coordinate on the unit circle, well, what would the angle measure in degrees have to be to give us that coordinate? And that's going to be 112.0243. 112.0243 degrees. And again, it is a second quadrant angle, just as we can anticipate from the radian measure. Keep in mind, pi over 2 is at 90 degrees. Pi is at 180 degrees, so somewhere between pi over 2 and pi, somewhere between 90 and 180. And then the inverse tangent of 7/5. And there we go, 54.4623 degrees. 0.4623. 623 degrees. Okay. Now, we talked about this issue with interval, restricting to specific intervals because it's required to make our functions one-to-one. We chose the intervals we wanted, those restricted domains for our trig functions, and hence the restricted ranges for our inverse trig functions, so that we could meet the requirement to be one-to-one. But as we've established, as we look at the unit circle, there are multiple locations where you get specific trigonometric values. So for instance, a sine of 1/2. One of the locations where you get a sine of 1/2 is going to be at pi over 6 radians or 30 degrees. Well, another location on the unit circle where you get a sine of 1/2 is going to be 5 pi over 6 radians or 150 degrees. If we're just using the inverse sine function to determine what angle gives us a sine of 1/2, well, the inverse sine function is going to tell us it has to be pi over 6. But depending upon the situation we're in, 5 pi over 6 may be the actual angle we want to address our particular application. So in other words, the inverse trig function may not give us the whole story. It certainly gives us a way to solve for angles, but sometimes we may want the other angle in the unit circle that gives us a particular trigonometric value. So that's what we're going to look at next. What if we have information about the angle, about its particular values, but we don't specifically want to find the angle corresponding to what our inverse function gives us? We want to find an angle that matches that's in another quadrant. We're going to look at this particular situation. So we're going to do a little bit more approximation, but we're going to deal a little bit more with this issue of quadrant. The quadrants we're restricted to versus maybe a different quadrant that we want. So our directions are to use a calculator to approximate the degree measure. So if we're in degrees, we want our answer in degrees. So the degree measure to 1 decimal place, or radian measure, here we're in radians, to 4 places for our angle theta, our unknown, that's subject to the given conditions. So we're going to approximate the value of the angle based on the information we know about this angle. Okay, so for our first angle, unknown, theta, that's what we're trying to solve for. We've been told that its cosine, the cosine of this angle, is going to be -8/11, and specifically this angle is between 180 degrees and 270 degrees. In other words, the angle we want is going to be in quadrant 3. Okay. Now, what do we know about cosine and getting a cosine that's going to be negative? Well, if we're talking about the unit circle, think of this as representing the unit circle. If we're talking about the unit circle, then we know the locations where we could get a cosine that's negative are going to be in the second quadrant and in the third quadrant. Cosine corresponds to our x-coordinate, and those are the 2 quadrants where our x-coordinate is negative. Now, if we're going to use an inverse trig function to evaluate, how would that work here? Well, anytime we want to eliminate a function, reverse a function, an inverse function can be used. So if the idea is that we want to solve for theta, theta is inside the cosine function. If we want to solve for theta, well, we have to get rid of cosine. You cannot divide COS. COS is not a number. You can't divide it. COS represents what you can think of as an operation. You have to undo that operation, the cosine operation, if you want to think of it that way. Well, in order to undo a cosine, you would take an inverse cosine. Inverse cosine reverses cosine. So in general, if I were going to solve for this unknown, I would take the inverse cosine of each side of this equation. And again, I'm doing this so that I reverse that cosine function so that I undo it and isolate my unknown theta. But whatever I do to one side, I have to do to the other side as well. Okay. So that isolates my theta, inverse cosine and cosine reverse one another. So that means theta is equal to the inverse cosine of negative 8 over 11. And we could plug that into the calculator, okay, but that's not the full story. What do we know about inverse cosine? Well, we know inverse cosine has a restricted range from 0 to pi. So in order to define the inverse cosine function, we took the domain of cosine, which is technically all real numbers, and we restricted it so that we're only getting cosine values one time, we're not getting any repeats. All the positive cosine values are represented in the first quadrant, and all of the negative cosine values are represented in the second quadrant. So we restricted our cosine's domain to 0 to pi, and as such, the outputs we get when we take an inverse cosine are going to be either an angle in the first or the second quadrant. So this particular value right here, inverse cosine of negative 8 over 11, that is actually an angle in the second quadrant, because that's going to be the corresponding quadrant associated with inverse cosine where we get negative values. Well, here's the problem though. The angle we want is supposed to be between 180 degrees and 270 degrees. Well, let's see what this actually is though. So we want it in degrees. Let's go ahead and approximate this and see what this angle is going to be. So I'm going to pull up my calculator again. Okay, clear this out. Now we're in degrees. Let's check the mode. We're in degree mode still. Okay, so we're taking the inverse cosine of negative 8 over 11. And that's going to be the angle we get. So far, and at the end we're going to approximate to one place. So here we can just approximate to one place as well. So approximately 136.7 degrees. And that is going to be almost halfway here in the second quadrant. So that's what we have so far. Okay. What we actually want though is an angle that's in the third quadrant that also has the same value for cosine. Well, what do we know about cosine? We know cosine corresponds to the x value. So at this particular location, we have a particular x value, we have a particular y value. What we're interested in is the x value. What we want to find is the corresponding angle in the third quadrant where the x value is the same. But in this case, the y would be negative. What we're focused on is the fact that the x value is the same. So this is our actual angle theta. This is the actual theta we want. This is the angle that we get from the inverse trig function. The larger angle that's between 180 and 270 is going to be the angle that we actually want. Well, the question is, what is that angle? How do we determine what it is? Well, what do we know about these two angles? What do they have in common? Well, they have to have the same cosine. What we know about angles that have trig values in common is that in order to have those values in common, they have to have the same reference angle. In other words, this angle and this angle are going to be the same. They have to be the same. So if I can determine what this distance is right here, what this amount of rotation is, then I can just take 180 degrees and I can add that on, and that's going to give me the actual value for my angle that I want. So I know that the angle I got from the inverse cosine was 136.7 degrees. Well, what is its reference angle? How far is that in terms of rotation from the x-axis? Well, the reference angle here is going to be 180 degrees minus 136.7 degrees. And now we're just working in approximations, so use the approximation. So 180 minus 136.7, that's going to be 43.3 degrees. If this angle, the angle we got from the inverse cosine, has the same cosine as the angle we actually want that's in the third quadrant, again, they have to have the same reference angle, this angle of 43.3 degrees. So if I were to take that halfway rotation and then add on that additional amount, what we call the reference angle, that's going to take me to the angle that I want. So the actual theta, I'll label this as the actual theta is going to be 180 degrees, that halfway rotation, plus this common reference angle, the reference angle we got from the inverse cosine angle, 180 plus that matching reference angle, so plus 43.3 degrees. So 43.3 plus 180 is going to give us 223.3 degrees. That's going to be the actual angle we want. So before we check this in the calculator, let's just go through the procedure once again. There was a lot going on here. Okay, so we wanted to determine the angle that meets these requirements. We know its cosine has to be -8/11, and the angle we want is going to be a third quadrant angle. Well, first off, that at least makes sense. A third quadrant angle will have a negative cosine, so there should be some angle that makes this equation true. Now, we cannot identify an angle that has that value for its cosine directly from the unit circle because we don't have this particular coordinate labeled on the unit circle. So the only way to solve for theta, since we're willing to approximate, is to use the inverse cosine. Inverse cosine will reverse the cosine function and allow us to isolate our angle. And specifically, whenever we take an inverse cosine of a value, it's giving us out the angle that we want that has that as its cosine. So if the cosine of theta is -8/11, then the angle itself is going to be the inverse cosine of that particular coordinate. Again, what we can think of as a unit circle coordinate, just one we don't see labeled. Well, we know whenever we take an inverse cosine, it's either going to give us a first quadrant or a second quadrant angle depending on what we're applying it to. If we're applying it to a negative value, we know it's going to correspond to a second quadrant angle, just by default based on how we've defined inverse cosine. And sure enough, if we plug this into the calculator and approximate, that was approximately 136.7 degrees. So that's the value we get from our inverse cosine, but it doesn't meet all our requirements. So this particular angle will have roughly -8/11 as its cosine, but it doesn't meet the second requirement that the angle has to be between 180 and 270 degrees. But what we know about any angle that has matching trig values is that it has the same reference angle. That's the idea behind reference angles. Reference angles are angles in the first quadrant that give us all the values we want that we then can just match into the other quadrants based on flipping signs, making things positive versus negative, etc. So the reference angle has to be the same. If these two angles correspond to the same x value, then we know that they also have to be the same distance away from this x-axis, this negative x-axis, what we think of as 180 degrees. So we found the reference angle, so we know how far apart this is. The reference angle, by subtracting from 180, was 43.3 degrees. And so if we take the halfway rotation and add on that additional amount, that's going to take us to the actual angle we want that's in the third quadrant. So 180, my halfway rotation, plus that common reference angle takes me to 223.3 degrees. So that's going to be the angle I want. Now I should be able to check my work here, 223.3 degrees. What we're saying is that this angle supposedly has a cosine of -8/11, and of course we know that it meets the requirement to be within our particular interval in question. But let's check the actual cosine. So cosine of 223.3 degrees is going to be -0.7277 and then some. What we want to know is that the same thing as -8/11? Well, it's not going to be exact because we rounded. Here's where we rounded. This was the first place we rounded, and then everything else, there wasn't really any rounding. We just carried through the rounding that we did here. But they should be pretty close, just based on that we only rounded a little bit. So -8/11, really close, basically the same value. So that's a verification that we meet the first requirement, this angle fits this requirement, and of course it also meets the requirement for our particular interval. Okay, let's look at another one, tangent. Okay, tangent, we know when we take an inverse tangent, it's going to be a first quadrant angle or a fourth quadrant angle. Okay, so we've been told here that whatever our angle is, its tangent is -9/7. Okay, but we want an angle specifically that's in the interval from pi/2 to pi. In other words, a second quadrant angle. Okay, so we can't correspond this to anything specifically labeled on the unit circle. We don't see anything labeled as a -9/7, so we can't just pick a value off the unit circle and say this is the angle we want because the angle is our unknown. So instead, we're going to use the inverse tangent to solve for theta. So apply the inverse tangent to both sides of the equation. Again, whatever you do on one side, you have to do on the other. Inverse tangent of -9/7. Okay, on the left-hand side, inverse tangent reverses, undoes tangent, and so we're just left with theta, and theta is equal to the inverse tangent of -9/7. Now, because it's now defined in terms of inverse tangent, we know that it has to be in one of two quadrants. Okay, if this were a positive value, it would correspond to an angle in the first quadrant, but since it's a negative value, it's going to correspond to an angle in the fourth quadrant, but not an angle from 3pi/2 to 2 pi, an angle from 0 to -pi/2, a negative angle. So this is going to correspond to quadrant 4, but negative. And we can verify this by getting the approximation. Now for radian measures, we wanted to approximate to 4 decimal places. And because our inequality is in radians, we know we want our angle here to be in radians as well. So let's change over to radian mode first. Okay, so now we're in radian mode. What we should get now is a negative angle. So we're taking the inverse tangent of -9/7. Okay, sure enough, negative angle. So to 4 decimal places, that's going to be -0.9098. Okay, but again, that is a fourth quadrant angle, and the angle we want is going to be a second quadrant angle. So without knowing specifically where it is, it's just somewhere in the fourth quadrant. So this is the actual angle we found. Okay, what we want is going to be a matching angle in the second quadrant that has the same tangent value. So if we think of this being a particular x, which will be positive, and a y, which will be negative, what we're looking for is the angle that's going to correspond to the same values, except the x will be negative and the y will be positive. Because they otherwise have the same values, when we take the ratio, we're going to get the same ratio, and this ratio should come out to -9/7. Now again, because these angles have the same value for tangent, they have the same trigonometric value, we know that they have to have the same reference angle. And as it turns out, even though this is a negative angle, if we were to think of it in positive terms, that would be our reference angle. This would be our actual reference angle. So this angle and this angle, those would be our reference angles. Those should be the same because, again, these two angles, this angle and then the actual angle we want, have the same trig values, so they have to have the same reference angle. So our reference angle, if this is -0.9098 radians, the reference angle is just going to be the positive version of that. So 0.9098 radians. Well, what we want to know then is what is this particular angle, as labeled in the second quadrant, that has this as its reference angle. Well, if we take the halfway rotation to pi and take the difference between that and our reference angle, that's going to give us the particular angle we want. So our actual theta is going to be pi, that halfway rotation, minus the amount of rotation represented by our reference angle, so 0.9098. And pi, of course, because we're in radians. So pi minus 0.9098, and then to 4 decimal places, 2.2318 radians. Okay, so again, same idea as before. We had information about our angle. The inverse trig function solves for our angle, but it doesn't put it in the correct quadrant. So we have to match the angle we find via the inverse function to an angle in another quadrant based on the fact that they have to have the same reference angle. They have the same trig values. They have to have the same reference angle. So let's verify that this particular angle does meet our requirement. Now it is between pi over 2 and pi. Pi is 3.14, pi over 2 is half of that. So 2.23 is somewhere between those. But we need to verify that its tangent is correct. So let's see what the tangent is for this particular value. So 2.2318, we're taking its tangent. Okay, it's negative, that's good. What is negative 9 over 7? Is it close to that number? Yes, it is close to that number. So again, we rounded about halfway through the problem. That explains the difference at the very end, but the fact that the numbers are really close together is a good confirmation that our answer makes sense. Okay, now let's talk a little bit about composition. We did a little bit of composition there when we applied the inverse trig function to the original function to reverse it, to undo it. In general, composition is a little bit more complicated than that, though. So in this case, we were applying things to an unknown, and then we adjusted based on the quadrant we were in. That's not always going to be as straightforward as cosine and inverse cosine reverse one another and they just cancel out. Now, normally, when we compose a function and its inverse, they cancel out, for lack of a better way of putting it. They reverse one another. They undo one another. So if we apply a function to its inverse, then they reverse one another, and we're just left with whatever the input was. And then same thing the other way around. If we apply the inverse to the original function, they will also reverse one another. Now this is assuming that we don't have any preliminary issues with either of these functions. But trig functions were not that simple. Remember, the trig functions, we had issues early on because they were not one-to-one. So everything we can normally do with inverses couldn't be done initially. We had to sort of provide a workaround to determining how those inverse trig functions would work. So because we restricted the domain for those original trig functions, this rule does not always work as cleanly as we would like. It depends upon the value of x. Does it actually fall already within those restrictions or not? If it doesn't fall within those restrictions already, then things may not cancel out the way we expect them to. So when we normally compose functions together, we compose a function and its inverse, we understand that they just reverse one another, they cancel out. Because that's not necessarily the case with a trigonometric function and its inverse, whenever we're composing two functions together, we need to get in the habit of applying each function in the composition one at a time. Starting on the inside, of course. So order of operations says we always start on the inside of parentheses and then work our way out. Same kind of thing with composition. So let's try a few of these. Now, some of these problems can be done just using the unit circle. Whenever we have values, either an angle or coordinates that we can find from the unit circle, then we can use the unit circle. If we ever have an angle or coordinates that are not defined on the unit circle, or that aren't just labeled, that we can't see on the unit circle, then we're going to have to use some other strategies, and we'll get to that. Okay, first off, inverse sine of the sine of 5 pi over 4. Now first off, 5 pi over 4 does not fall within that standard interval that we're looking at when we're talking about the restricted domain for sine. When we were talking about sine, we restricted its domain to negative pi over 2 to pi over 2 to the first and fourth quadrant. Okay, so 5 pi over 4 does not fall within that particular range, right? So this is not going to be as simple as things just cancel out. So rather than trying to just cancel out and say that the answer is 5 pi over 4, we have to work with each of these functions one at a time, starting on the inside. So sine of 5 pi over 4, the y value at 5 pi over 4, is going to be negative root 2 over 2. So we're taking the inverse sine of negative root 2 over 2. So this again asks the question, where on the unit circle do we have a sine of negative root 2 over 2, but specifically within the interval we want from negative pi over 2 to pi over 2? Well, if it's negative, is that the sine has a negative value. We know we're looking at a fourth quadrant angle. Remember, those are going to be negative angles, not 3 pi over 2 to 2 pi, but 0, and then rotated backwards to negative pi over 2. So the negative angle, where we have a sine, a y value, of negative root 2 over 2 is going to be negative pi over 4. So notice our final answer does not match the original input inside the composition. And again, that's because this angle was outside of that range of values that we originally looked at. And so they didn't just cancel out the way we would normally like. Okay, inverse tangent of negative pi. Okay, same idea. Start on the inside, work our way out. Now don't be alarmed by this negative pi. Negative pi and pi are actually co-terminal angles. So negative pi, we just end up at the negative x-axis, but we've rotated backwards. But the coordinates are the same as they are if we're just looking at regular old pi. So the tangent at negative pi, we're then applying the inverse tangent to whatever that is. The tangent at negative pi, it's going to be our y coordinate over our x coordinate. So the y coordinate over the x coordinate is going to be 0 over negative 1, which is going to be 0. So now we're taking the inverse tangent of 0. So we're asking the question, if the tangent has a value of 0, well, what angle in radians would we need within the particular interval we want, from negative pi over 2 to pi over 2, not including? Well, the only location where that happens in that interval is going to be at 0 radians. So the answer is going to be 0. Now, be careful when you look at these two zeros. These two zeros mean different things. This 0 means coordinates. This is referencing coordinates on the unit circle, specifically y divided by x. This 0 is an angle in radians. They don't mean the same thing. So don't think that somehow just tangent inverse went away. These two zeros mean two very different things in terms of looking at those numbers on the unit circle. Okay, let's try another one. Now we're going to apply an inverse function first and then a trig function second, and we'll see what happens. So inverse cosine of negative 1/2 starting on the inside. So we're asking the question, where on the unit circle is the cosine negative 1/2, specifically within the interval we want from 0 to pi? Well, the angle that's going to match up to a cosine of negative 1/2 is going to be 2 pi over 3. So this is going to be the cosine of 2 pi over 3, evaluating our inverse function first. And so then we take the cosine of 2 pi over 3. So the x-coordinate at the radian measure 2 pi over 3 is going to be negative 1/2. So notice in this case, they did actually just reverse one another, and we did end up with that original input that we started with. It's because of the ordering here. So rather than trying to memorize a pattern for when they do and when they don't just cancel out, it's better just to evaluate one function at a time, start on the inside, work your way out, and then go from there. So with these three examples, we either had a radian measure that we could find on the unit circle, or for this last one, we had coordinates that we could find on the unit circle. It's possible we're going to do problems like this that don't actually correspond to values that are written out, labeled on our unit circle. And if this is the case, we're going to have to do a workaround. We have to think, number one, about what our inverse function represents, what it gives us, and then strategies we can use to take that information and interpret that information. Okay, now as with any composition, here we're going to start on the inside and work our way out. So inverse tangent of -8/15. In other words, we're asking the question, if the tangent has a value of -8/15, well, what angle would we need for that to be the value? Well, unfortunately, this is not a number that's labeled on the unit circle. We don't see a -8/15 on the unit circle, and we can't get that as a ratio of any of the things we already have labeled. So it's not going to be as simple as looking at the values on the unit circle. So we're going to have to do a workaround. What we need to think of, though, is what does this actually represent? Well, this represents coordinates. This represents some type of unit circle coordinates, not ones that are labeled. And when we take the inverse tangent of this value, we're getting out an angle. So all of this expression represents some unknown angle, and let's just call it theta. So we're defining our unknown, theta. We don't know what it is because we can't determine it from the unit circle. Theta is going to be defined as the inverse tangent of -8/15. Now, because we're defining it in terms of this inverse function, automatically, even though we don't know what the angle is, we know what quadrant it's going to be in. Inverse tangent either takes us to the first or the fourth quadrant. And since we're taking the inverse tangent of a negative, we know that theta has to be an angle that's in the fourth quadrant, specifically a negative angle. So I'm going to go ahead and take that angle and I'm going to draw it where I know it needs to be, there in the fourth quadrant. So specifically, it'll be an angle where we've rotated backwards. Okay. Well, we still don't know anything about what theta actually is. But whenever an angle value is unknown, one good strategy we can apply is to draw a right triangle to represent the information we do know. Well, how would we draw a right triangle here? To draw a right triangle, we either need to have some side lengths, or alternatively, if we know one of the trigonometric values of our angle, that also gives us information about our side lengths. So we haven't been given side lengths directly here. We've been given them kind of in reverse. So if theta is equal to the inverse tangent of this value, another way of saying that communicates the same information is that tangent of theta is equal to -8/15. These two pieces of information mean the same thing. So if the tangent of theta is -8/15, then theta has to be defined as the inverse tangent of -8/15, as long as we know what quadrant we're in based on the fact that we're talking specifically about inverse tangent that has some specific restrictions. Well, here, now we have a specific trigonometric value for our angle theta. If we have a trig value, we can draw a triangle. And if we can draw a triangle, we can pretty much determine anything we want from there. So our tangent of theta is defined as -8/15, opposite over adjacent. Now, because of the quadrant we're in, we know that our x is positive and our y is negative. So our opposite side is going to be 8, but it's not going to be just 8, it's going to be -8, based on the fact that we're in this quadrant where the y coordinate is negative. And then our adjacent side, our x in this case, is going to be +15. Well, how does this help us? Well, go back to what we originally had. We were evaluating an inverse trig function that we couldn't evaluate using the unit circle So we wrote down information, we know this represents an angle, we determined a trig value for this angle. But if we go back to that original problem, this is now some unknown angle that we're calling theta, which means we're now taking the sine of this theta, whatever theta is. Well, if we have a triangle, we can find the sine based on the angle we have labeled in that triangle. The only thing we still need is the length of that additional side, in this case the hypotenuse. Well, 15 and 8 actually represent two parts of a Pythagorean triple. The other side length is going to be 17. You can verify that with your Pythagorean theorem. Remember, this length is always going to be a positive number. The only things that can be negative are the coordinates. So based on that, we can find our sine. Sine is going to be our opposite over our hypotenuse. So the sine is going to be negative 8 over 17. So notice, even though we didn't know anything specifically about theta itself, and we still don't know officially what theta is, we don't have an exact number, we'd have to just approximate, we actually could solve the problem just based on the fact that we understood what an inverse function means and how it corresponds to trigonometric information, and then how we can label a triangle from there. Now let's do one more problem like that. Okay, cosecant of inverse cosine. Now, negative 3 over 7, we're taking the inverse cosine of negative 3 over 7, so we're asking the question, if this is the value for cosine, well, what angle corresponded to that particular value for cosine, specifically in the first or second quadrant, based on the fact that we're looking at inverse cosine. Again, negative 3 over 7, not something we can quickly identify from the unit circle, from everything we have labeled. So it's just some unknown angle theta. So theta is equal to our inverse cosine of negative 3 over 7. We don't know exactly what theta is, but since it corresponds to the inverse cosine of a negative, inverse cosine either takes us to the first or the second quadrant. Since we're looking at a negative coordinate, we know we're talking about the second quadrant. So that means whatever theta is, it's going to be in the second quadrant. That's going to be our theta. So this is the actual theta, some angle in the second quadrant. Okay. Now, from this piece of information, another way of saying this, aside from this issue with quadrant, another way of saying this is that the cosine of theta is equal to negative 3 over 7. These two pieces of information are essentially the same. And if I know this trig ratio, then I know how to label a triangle from it. So this is our actual theta, but we know at this point, in order to draw a triangle, in order to label sides, that we actually use what we think of as the reference angle, the acute angle that matches up with this particular obtuse angle. So the cosine of our angle, adjacent over hypotenuse, is going to be negative 3 over 7. Now, which one's negative, which is positive? The hypotenuse must always be positive. So 7 is going to be the positive coordinate, and this is going to have to be negative 3. And that also makes sense based on the quadrant we're in, since second quadrant angles are going to have negative x values and then positive y values. Now we need to find the length of the other side, and this one's not part of a Pythagorean triple, so we're just going to have to solve for it. So negative 3 quantity squared plus our unknown y squared is equal to 7 squared. So 9 plus y squared is equal to 49. So y squared is equal to 49 minus 9, which is 40. So y is equal to the positive or negative square root of 40. Well, which one is it, positive or negative? Well, here we're in the second quadrant. Our x is going to, or excuse me, our y is going to be positive, okay? And then we need to simplify the square root of 40. So although 40 is not a perfect square, the perfect square 4 divides into it. And so we take the square root of 4 and we get a 2. And we're left over with that factor of 10. And again, we keep the positive because of the quadrant we're in. So this side has a length of 2 root 10. Well, if we have a triangle, we have everything we need to know about all of our trigonometric ratios. So we represented our unknown angle in terms of this particular inverse trig function. So what we now have is the cosecant of that unknown theta. And if we have a triangle representing theta, we can find the cosecant. So if sine is opposite over hypotenuse, then cosecant is going to be hypotenuse over opposite. So hypotenuse over opposite is going to be 7 over 2 root 10. Rationalize it. So that's going to be 7 times the square root of 10 over 2 times 10, which is going to be 7 root 10 over 20. And there we go. So definitely spend some time practicing with your inverse trig functions with and without the unit circle. Again, don't become too dependent upon the unit circle because you're not always going to have one available. Being able to visualize it, have a sense of where things are, particularly with respect to this issue with quadrants, with intervals, when we defined these inverse trig functions, that's going to become very, very important. So inverse trig functions are going to be extremely versatile. We're going to use these a lot in applied problems. So if we're looking for side lengths in general, side lengths, we can use actual trig functions to solve for side lengths. Anytime we want to solve for an angle, in general, we're going to use an inverse trig function. So we're going to encounter these more and more, particularly as we look at ways that we can use trig in application.